This is lecture 6C for Calculus 2. Some examples of the calculation of volumes of solids. Before we go through the examples, I think it'd be a good idea just to remember what these different methods are. The first is the slab method. Okay, here's the slab method. In the slab method, you take the object as though it were a loaf of bread, put it on the x-axis between x equal a and x equal b, and then you slice it up. And each slice has a cross-sectional area. You can see the slice, the area of that slice, at the face of that slice right there. That's a cross-sectional area. And this area varies with x. When x equals b, it's going to have one area. When x is over here in the middle, it's going to have a much larger area. Here x goes back to kind of a small area on this object. The volume is the integral, the definite integral from a to b, going from a to b of this area, a of x dx. That's the slab method. In a variation of the slab method, we have the solid of revolution. A solid of revolution is skewered onto the x-axis, right? And varies from a to b, whatever a to b happens to be. In this case, it's minus a to plus a, but that's fine. Some limits of integration. And then just like in the slab method, you're integrating the cross-sectional areas. The cross-sectional area of the solid of revolution, as you can see here, is a circle because of its symmetry and because of how you place it on the x-axis. It is a circular cross-section, and the area is pi r squared, where r is right here. It's a value of y, and that has to be worked out in this case. That expression there has to be worked out. But this is the slab area, pi r squared, and r is some function of x. You see r is 0 here, r is 0 here, and you write here r is equal to the radius on the sphere, which is a, and then it decreases as you move. So it's smaller and smaller. So that's a solid of revolution. Here's a variation on the solid of revolution, and this is the washer method. In the washer method, you have actually two solids of revolution. One is created by the outside edge of the figure. It has to be symmetric, and its cross-sectional areas are all circles. Right. Here's some radius r. Then it has a hollowed-out core that also has the same symmetry. It's symmetric with respect to the same axis as the outside edge, and it has a radius, I'm going to say here, of little r. So the method of finding the volume of this washer is to take the volume of the outer surface and subtract off the inner core that got subtracted off from the solid itself. Because it's a solid of revolution, the surface areas are pi r squared, and r can vary with x. Pi little r squared, and again little r can vary with x. You can see it's sort of flared at this end. And you subtract those two, you can combine that as one integral. So pi is here. These are the limits of that the figure's occupying in x. R squared is the outer radius, little r is the inner radius, and they both could vary with x. That's your washer method. Here's the shell method. In the shell method, you cut this thing up as though you had like a cookie cutter, and you cut it up into slices, and the volume is the sum of all of these cylindrical slices that you've cut it up into. Okay, what is the volume of the cylinder? All right, it's 2 pi x. 2 pi x will give it the radius all the way around it. All right. The width is delta x, or dx, and the height is some function of x. It's really this y, which is some function of x. So that's the height of the cylinder, and that's the shell method. So here's an example of the slab method. The slab method, we're going to compute the area of this pyramid, and the pyramid has a square base and 3. The sides, when x equals 3, are 3. It's a 3 by 3, and then it decreases linearly to when x equals 0. Kind of fell off the end of the scan here. When x equals 0, the cross-sectional area would be 0. So here's a typical cross-sectional area right here. So the area in this case is x squared, because x is varying. The length of the side, when x equals 0, the side is 0. When x equals 3, the side is 3, and it's a linear variation, therefore the side equals x. So area is the side squared, so it's x squared because it's a square. Okay. And this slide just says, has written what I was trying to say in the other case. The length of each side varies linearly with x, so the side equals x. The cross-sectional area of each slab is a square, so the cross-sectional area is x squared. The volume is the integral from 0 to 3 of the cross-sectional areas by dx. Okay, 0 to 3, x squared dx, use the power rule, and you get an answer. You see, carrying out the integration on these is usually fairly trivial for many figures of many solids. The setup is what the problem is. Now we'll do a solid of revolution, in this case a sphere. So here's the sphere. It's varying from minus a to a, has a radius of a. So the question is, what is this? Here's the radius, and it's a value of y, which is some function of x. And what is the function of x? Well, how is this circle defined? All right, it's a sphere, so we've got a squared is x squared plus y squared. I can solve for y, and I get the square root of a squared minus x squared. But an expression here would be pi r squared, but r is y, so pi y squared. So pi, taking the square of a square root, gets rid of it, times a squared minus x squared. Again, setup is what requires a little thought. Now I know the cross-sectional area, and here's the cross-sectional area varying with x. All I have to do is integrate over it. So again, the cross-sectional area of the sphere, parallel to the x-axis, is a circle of radius a. Solve for y, and we get this. The cross-sectional area is pi r squared, but that's really pi y squared. Taking the square of that square root gets rid of it, and here's our expression for the area. The volume then is the integral from minus a to a of the area times dx. So for area, I substitute pi times the quantity a squared minus x squared. Carrying out the integration, get 4/3 pi a cubed, which is what is expected for the area of a sphere of radius a. Here is an example of a displaced vertical solid of revolution. The one I showed you before was symmetric about the x-axis. This is symmetric about the line, the vertical line x equals 3. But still, every cross-sectional area is a circle. Right? So the cross-sectional area is 2 minus y squared. That's given here. So as y varies, this radius varies. When we're up here to the square root of 2, then the radius is 0. So if r equals 2y squared, minus y squared, 2 minus square root of 2 squared equals 0. So it's 0 here. It's also 0 down here, and it varies with y. So we're going to be integrating in y from minus pi over 2 to pi over 2. So now we've done the whole thing of rotating it and displacing it, but you can see it's basically the same procedure. I'm going to take the volume, and the volume is going to go from y1 to y2 of the area, which varies with y, times dy. Because it's a solid of revolution, the areas are circles. So y1 to y2 of pi r squared dy, and here's my expression for r. And this is just the same thing typed out. The area is pi r squared, so it's pi times 2 minus y squared. I have to square that. The volume, and then I can use symmetry, but the volume is the integral from y1 to y2, in this case, plus or minus square root of 2, of the areas. It varies with y, dy. In this case, it is a circle, circular cross-section, so it's pi r squared dy, and you see how that's written out right in here. You can use symmetry because this figure was symmetric about the x-axis as well, and just do half of it, go from minus 2 to square root of 2, and multiply the result by 2 will give you the whole volume of that surface, of that solid of revolution. And again, you're integrating with respect to y. And here is a washer example. In this case, you have this napkin holder, and it was a sphere, but then there was an inner core cut out of it. And you want to find the volume. Now, why would you want to find the volume? If you were working for a plastics manufacturer who was manufacturing 100 million of these, you would like to know the volume of plastic that would have to be molded to make each one of them. If you're working with wood, it wouldn't matter too much because you're coring out the inside and, I don't know, making plywood out of what you have left over. But for plastics, you would really want to know the volume of plastics that would go into making up this napkin ring. Okay, so how are we going to do it? Well, first of all, we know that, let's say that R is the radius of the whole outside sphere. Right. And this radius varies. Its cross-sectional area, okay, is circular, and it's going to vary from 0 when it's at H to R when it's right here. So doing the same thing as for the sphere. Remember the sphere example? The outer radius, which would be the outer radius right here, looking at this blue, is going to be the outer radius. Whoops, I ran out of room. Is the square root of big R squared, which is the radius of the whole sphere before anything was cut off of it, minus y. And what I've done is I put a coordinate system on this right like that. Here's my y-axis, and here's my x-axis. Let's say the inner radius is constant at little r. That's little r right there, and it's constant. That's the inner radius. Okay, the height is going to be h, as you can see. So when you do these problems, just like any problem that has any kind of anything you can draw it, sketch it out, and then put on your coordinate system. And that determines how you're going to integrate. Right? Because I put the 0 here, you see I have symmetry about the x-axis. So when I originally start, I integrate from minus h to h. Ooh, I just made, that should have been h over 2. Okay, let me fix that. Minus h over 2 to h over 2. But I can do 2 of them. I mean, I can just do half of it, the problem, from 0 to h over 2, and multiply by 2 to get the same result. And so here's the washer method. The volume is the integral of pi times the outer radius squared minus pi times the inner radius squared. And you can factor out the pi and put it outside. That's where the 2 came from, was because we're only doing half the integral, half of the surface, and multiplying by 2 to get the other part. I'm giving you here the example of using the shell method to calculate the torus. Actually, there's something like 78 methods to calculate the volume of a torus. Torus is a donut or a ring, however you want to think about it. But I'm going to show you a one-liner. Here's the one-liner right here. And this is how I do it. You see where the circle is? Okay, cut it. Now I've got the thing cut, and I stretch it out. When I stretch it out, it becomes a sausage. Oh, my perspective's all wrong on it. I'm sorry. Okay, that's a little bit better. Here's my sausage. All right, how long is this thing? Well, it's the whole length all the way around here. So it's 2 pi times big R. I should go back and explain to you what I'm using. All right, and then what is the radius of this? It's little r. What is the volume of this thing? It is pi r squared times 2 pi r, because 2 pi r is the height. This is so you took this ring, when you stretch it out, it becomes a cylinder. That's all. You just took it and I broke it in half and I pulled it and I unwrapped it. So here I've got the volume right here. Pi r squared, that's the base, times the height, which is 2 pi r. That's the volume of the torus. Let me go back and explain to you how what big R and little r mean. I'll take all the writing off. All right. Big R is the radius from the center of the ring to the middle of it. Little r, right here, is the radius associated with where the material is itself, the circular ring, part of the ring. So if this was gold, the little r has to do with the gold section of it. Big R has to do from the center of the ring out to the middle of where the gold is or where the material is. So you see what I'm talking about. I hope that you're going to take this, cut it at that circle that I showed you there. You unwrap it and you get a cylinder. Right? What is the volume of a cylinder? It's pi r squared. It's the area of the base times the height. But the height is 2 pi times big R, because that is the height of it when it's unwrapped is this distance all the way around here. 2 pi big R.